Hi class, this is Dr. O'Connor. In this video, I'm going to talk about buffers and titrations. This will be the last video for chapter 10. So a buffer is a solution of a weak acid and its conjugate base that will resist pH changes if additional amounts of acid or base are added. So it'll maintain the pH within a small range if acid or base is added. We have this blue line that corresponds to pure water, and the red line corresponds to a buffer. Actually, this is an acetic acid, so acetic acid acetate buffer. Okay, the solution is 0.1 molar in acetic acid and 0.1 molar in acetate ion. So to prepare the buffer, you would start with acetic acid, and then you would add the acetate ion, and you would use sodium acetate or some ionic compound that contains acetate ion. Okay. So here we see this blue line here, and we can see as we add, we'll start right here. Okay, so as we add, let's say, base hydroxide ion, notice that the pH increases by quite a bit. And also, if we were to add acid, so additional hydronium ion, the pH decreases by quite a bit. So we see this range of a pH of 2 all the way up to 12. Now, if we were to add the same amounts of acid and base to the buffer, then we don't see much of a change in pH. In fact, the range is 4.68 to 4.85. And that's because the buffer is composed of an acid. The acid will react with any additional base that is added, and it is also composed of the acetate ion or the base, and that base will react with any additional acid that is added. So let's go ahead and write the equation for this. So we have our acetic acid, and we're in water, so we're aqueous here. And let me write that out. And so we have our acetate ion plus our hydronium ion. Okay, so again, you can see we have this buffer system. If we add base, then the acetic acid will react with the base. If we add acid, the acetate ion will react with the acid. So that's going to keep the pH at a fairly constant level. Now, let's go ahead and write Ka for this. And what we have is hydronium ion. And remember, we don't include water in the Ka expression. Okay? So let's go ahead and represent the base, in this case the acetate ion. We'll go ahead and represent that with a capital A, negative. And then the acid we'll just represent as Ha. So what I'm going to do is I'm going to rewrite this, and I'm going to solve for the hydronium ion concentration. So let's solve this expression for the hydronium ion concentration, and I'm going to substitute this for the base and Ha for the acid. So hydronium ion concentration then is going to be equal to the acid dissociation constant, okay, times the concentration of the acid over the concentration of the conjugate base. Okay, so we have an expression here that would allow us to determine the hydronium ion concentration. And we can see that if the concentration of acid is greater than the concentration of base, then we're going to have a higher concentration of hydronium ion, or a lower pH. If the concentration of base is greater than that of the acid, then we're going to have a smaller concentration of hydronium ion, or a higher pH. Now, I'm going to do something with this equation. I'm going to take the natural logarithm of both sides of the equation. All right, so let's go ahead and do that. So I'm going to take the negative log of both sides of this equation. So the negative log of hydronium ion is equal to, we'll say, the negative log of the acid dissociation constant, and then I'll take the negative log of this expression here. Okay, remember, negative log is the p function, so the negative log of hydronium ion concentration is the pH, and the negative log of Ka would be pKa. All right, and then because of the property of logarithms, I have this expression right here. And this is what you're going to need in order to determine the pH of a buffer system, or you can determine how much acid or how much base you would need. This, and again, I'm not going to go into the properties of logs here, just take my word that that is the equation. So here it is again, and this is called the Henderson-Hasselbalch Equation. And we're able to use this then to determine pH, or again, if you know the pH and the pKa, you can determine this ratio. If you know these concentrations here and pKa, you can determine pH. Okay, and so you can, depending on the information you know, then you can find either pH, pKa, acid concentration, or base concentration. So again, this is the conjugate base of the weak acid in the buffer. So in general, for a buffer to be effective, it must meet the following 4 conditions. Number 1, the effective pH range of a buffer will depend on the pKa of the acid and the ratio of acid to conjugate base. That means that the pKa for the weak acid should be very close to the desired pH of the buffer solution. The ratio of acid to base should be close to 1. The molar amounts of acid and base in the buffer should be approximately 10 times greater than the molar amounts of the added acid or base. So these are the 4 requirements for a buffer system. And again, I can't stress enough, a buffer is a solution that contains a weak acid and its conjugate base. There are 3 major buffer systems that manage the pH of body fluids. The first one is the carbonic acid bicarbonate. And here is the reaction here. So again, if additional acid was added to this buffer, it would be neutralized by the bicarbonate ion. And if additional base was added, it would be neutralized by the carbonic acid. The second buffer system for body fluids is a dihydrogen phosphate hydrogen phosphate buffer. So we have our dihydrogen phosphate. Again, that would neutralize any added base, and the hydrogen phosphate would neutralize any added acid. The third buffer system we won't talk about here, but it has to do with the properties of proteins. They can act as either proton acceptors or proton donors, and that depends on the pH of the medium or of the fluids. And we'll talk about this we'll talk about all three of these systems in Chem 252. So for now, let's continue on. And I'm going to ask you a question based on what I just told you. We have this table here, and we're asked which acid in the following table, they're all weak acids, would be appropriate for preparing a buffer that has a pH of 4.90. What did we say? pKa should be as close to the desired pH as possible. So 4.74, no, that'd be too low. 4.10, that'd be too low. But it looks like 4.89. So the best acid for this buffer would be propanoic acid. Let's do another problem here. We're told that the pH of a buffer solution that contains 0.1 molar acetic acid and 0.1 molar sodium acetate is 4.74. Write the Henderson-Hasselbalch equation for this buffer. Okay, so the Henderson-Hasselbalch equation is the pH is equal to pKa plus the log of this ratio, the conjugate base to the weak acid. So let's fill this in. We have a pH of 4.74. That's equal to pKa plus log, both are 0.1 molar. And notice this is log of 1, and log of 1 is equal to 0. Okay, because this is log base 10. 10 to the 0 is 1. So if this is equal to 0, then in this case, our pKa is equal to the pH. And that's true. When the ratio is equal to exactly 1, then pH is equal to the pKa of the acid. Okay? What is the pH of a buffer system that contains 0.2 molar hydrocyanic acid and 0.15 molar sodium cyanide? So we have the pKa of hydrocyanic acid is 9.31. Let's take a look at what we have. We have our Henderson-Hasselbalch equation. pH is equal to pKa, which is 9.31, plus the log of the concentration of the conjugate base. That would come from the sodium cyanide. That's 0.15 molar. And this is divided by the concentration of the acid, which is 0.2 molar. And we put this into our calculator, and I get a pH of 9.19. So practice some of those buffer problems. So the next topic that I'm going to talk about will be that of a titration. A titration is a procedure where we can determine the total acid or base concentration of a solution. In fact, there are different types of titrations, not just acid-base titrations, but we'll talk about acid-base titrations here. So a titration, I'm assuming that you've done these in the lab, but here let's say we're doing a titration involving sodium hydroxide and hydrochloric acid. Okay, so in the flask here, let's say I have an unknown concentration of hydrochloric acid, and in my burette I have the titrant, and the substance in the burette is the titrant, and that's the sodium hydroxide in this case. So the whole idea is this: we have a balanced equation for the acid-base neutralization, and let me put this in. So the equation is balanced, and that's important. You have to have a balanced equation. So I have a 1-to-1 mole ratio of acid to base. So the whole idea is, you know the concentration of the sodium hydroxide, which is the titrant. You know how many milliliters it will take to neutralize the HCl. How do you know that? We have to use something called an indicator. Indicators are also acids, bases, and they change color depending on the pH. So in this case here, we've added some phenolphthalein to the HCl. And phenolphthalein is colorless in acidic solution. So what we do is we start to add the titrant, the sodium hydroxide, until the pink color remains in solution. And that's the end of our titration. In fact, we call that the end point. That's where we see the color change. So now, from that information, we know the volume of titrant, we know the concentration of the titrant, we know the volume of the acid. We can determine the molarity of the acid, again, using our balance chemical equation. So when we do a titration, we find out the total acid concentration. You know, we could take the pH, but that only gives us the hydronium ion concentration and not the total acid concentration, because the total acid concentration is the sum of both dissociated and undissociated acid. We want to know how much acid is in that solution. Again, as I said, the end point of the titration is the color change when the neutralization is complete. Now, your book gives you these two formulas here. I don't use them, but I'll show them to you. But when we do the problems, I'm going to show you an easier way of doing these titration problems. And I think it's easier because you don't have to worry about remembering these things, and you don't have to convert back and forth. So anyway, when a titration involves a neutralization reaction where there's a 1-to-1 mole ratio of acid to base, then we can use this in order to determine, you know, if I know the molarity of the acid, the volume of the acid, and let's say I know the molarity of the base, I can determine the volume of base needed. Or again, if I know any three of these parameters, I can determine the fourth. Now, many times the coefficients for acid and base are not going to be 1-to-1. So in that case, they want you to use normality and equivalence of acid and base. Well, again, you can do that, but I would just assume use the stoichiometry skills that I learned a little earlier in the course. So that's how I'm going to show you. That's how I'll show you. I'll show you how to do the problems that way. So let's say we have sodium hydroxide and hydrochloric acid, okay? And so let's say we're given the volume of sodium hydroxide solution, and from the volume and the concentration of that, we can determine the moles of sodium hydroxide. Then what we need to do is use the coefficients in the balanced equation to relate moles of sodium hydroxide to moles of hydrochloric acid. Finally, once you determine the moles of hydrochloric acid, you can then determine the molarity by dividing the moles by the volume. Okay, so let's go ahead and do a couple of problems here. Here I'm told that titration of a 10 milliliter solution of ammonia requires 15 milliliters of 0.025 molar sulfuric acid solution. What is the molarity of the ammonia solution? Well, the first thing that I want to do is I want to write my equation for this. So I have sulfuric acid plus I have ammonia, and that's going to give me ammonium sulfate. And I need to balance, and of course this is all aqueous, so there is water here. But I need to balance this. I have 2 nitrogens on this side, so I have to balance this. So this is balanced. What we have is a 2-to-1 ratio of base to acid. So we're being asked, what is the molarity of the sodium ammonia solution? Well, what I need to do is determine the moles of sulfuric acid that were used for this neutralization. And I can do that because remember, molarity is moles over volume in liters. So I can solve for moles, that's equal to the molarity times the volume. So I have 15 milliliters. We'll convert that to liters, 0.015 liters, and the molarity is 0.025 molar. So this will give me the number of moles. I'll multiply that together. I have 0.025 times 0.015, and that gives me 3.75 times 10 to the -4 moles of sulfuric acid. So now that I know the moles of sulfuric acid, I can go ahead and relate that to the ammonia using my balanced equation. So I have 3.75 times 10 to the -4 moles of sulfuric acid. And from my equation, I know that 1 mole of sulfuric acid will react with 2 moles of ammonia. So let's see, I'll just multiply that by 2, and I end up with 7.5 times 10 to the -4 moles of ammonia. So now I can determine the molarity. I just take the moles of ammonia and I divide that by the 10 milliliters, but I have to convert that to liters. So that's 0.01 liters. And I get 0.0375 molar. Let's go on to the next problem. We're asked how many milliliters of 0.25 molar hydrochloric acid is required to neutralize 25 milliliters of 0.198 molar of sodium hydroxide. First, we write the balanced chemical equation, and I think we know this one by heart. We've used it so many times. And here's our neutralization. That's going to be water and sodium chloride. Okay, we have a 1-to-1 mole ratio of acid to base. First, let's find the moles of sodium hydroxide. And we can do that by multiplying the molarity times the volume in liters. So we have 0.198 molar sodium hydroxide. We'll multiply that by 0.025 liters. And I get 0.00495 moles of sodium hydroxide. So now I need to use my balanced chemical equation to relate the moles of sodium hydroxide to that of hydrochloric acid. So I have 0.00495 moles of sodium hydroxide, and we have a 1-to-1 mole ratio. So 1 mole of sodium hydroxide to 1 mole of HCl. So because it's a 1-to-1 mole ratio, the number of moles of HCl is the same. Okay, So anyway, I have in the problem, I was given the molarity of the HCl, and I determined the number of moles. They want to know how many milliliters of the HCl I need. Well, we know that molarity is equal to moles over volume, which is in liters. So I'm going to solve for the volume. So the volume in liters is going to be equal to the number of moles divided by the molarity. And let me erase this. That's going to be 0.00495 moles of hydrochloric acid divided by the molarity, which is 0.25 molar, and I get 0.0198 liters, but we want milliliters, so we multiply that by 1,000, and we would need 19.8 milliliters of hydrochloric acid. Well, that concludes chapter 10, and this is the last video for that. So if you have any questions, as always, please contact me. Otherwise, have a great weekend.